Okay, so last time we stopped at this point. We said that homogeneous coordinates are, they will make our job much easier than compared to non-homogeneous coordinates. And the modifications for homogeneous coordinates that we make are very simple actually. We talked about that. Find the attendance. Okay, we said that by doing this simple transformation, by just adding one more dimension to our two-dimensional vectors, we are still in the two-dimensional world, but we are representing our points with three-dimensional vectors, and we can do the same thing for three-dimensional world. In three-dimensional world, our vectors will be four-dimensional again. And if we do this, a number of procedures will become linear operations, linear matrix multiplication, etc. Also, it would be possible to talk about points at infinity now. And points at infinity is very convenient for us now. And we can do stuff like, what happens if I project a point from infinity to my image plane? Can I find its corresponding finite, not infinity, a finite point on my image plane? And we could do that. Last time we did that, okay? So I think we did a number of exercises like those. A number of exercises. One of them was this. We said that, okay, this is a number, okay, this is a line represented by 1, 0, minus 1. This is 0, 1, minus 1. And if I take the cross product of these two lines, I would get 1, 1, 1, which corresponds to this one, because from homogeneous coordinates to non-homogeneous coordinates, the transformation will give me 1, 1, 1, so it works. And the better example was this. If I find the intersection point of these two parallel lines, okay, usually the the geometry that they teach you in high school or middle school, they will tell you that these kind of lines, they don't intersect, they intersect at infinity, and that's it. But what is the point that these points are intersecting at? Okay, now we can find it. We say that, okay, take the cross product of these two lines, and I will get this, 0, 3, 0. Obviously, I cannot transform this point back to non-homogeneous coordinates, because 3, 0, 3 requires 0 over 0 and 3 over 0, which I cannot make. But I know that in homogeneous coordinates it's meaningful. So it's a point in infinity. I'm not saying that the point at infinity is a point in infinity, because there are infinitely many points at infinity, okay, and I get one of them. How many points are there at the infinity? There are infinitely many points, but they are all at the same line, which is this line. This is a line at infinity, okay? Line at infinity. So all the points add up to a line at infinity. How do I know that? Because, okay, this is line at infinity, right? Any point P, with if I cross product with L infinity, I should get a 0. Okay, so what kind of points are at infinity? It is all A, B zeros, right? So if this one is a 0, that means that it's a point at infinity. What is my line at infinity? It is 0, 0, and 1. And as you see, whatever I do, what kind of A, B values I have doesn't matter. It's going to be 0, right? Because A times 0 is 0, B times 0 is 0, 0 times 1. So I am saying that you cannot write a point at infinity that doesn't sit on this line. So that means that all the points at infinity should be should make up a line, and that's the line 0, 0, 1. Okay, good. So, and this one is good. Can somebody read this to me? Can somebody read this to me in English or Turkish? These are all the points in our non-homogeneous coordinates. Okay, complete this for me, rest of this for me. While you are doing that, I am going to this. Read it in Turkish or English.
Reel sayılarla ifade edebildiğimiz tüm vektörleri ve sonsuzdaki vektörün birleşimiyle şeyi kapsayabiliriz. Bütün noktaları.
Hangi nokta? Bir daha baştan söyle.
Reel sayılarla ifade edebildiğimiz...
Reel sayı değil bu. Reel sayı değil bu. Şu var. Ne demek? İki boyutlu demek. İki boyutlu non-homogeneous vektörler, iki boyutlu non-homogeneous koordinatlar
Ve işte sonsuzdaki vektörler.
Sonsuzdaki noktalar birleştiğim zaman homogeneous iki boyutlu noktalar gelir. Şunlar nasıl? These are the values that you represent with like x, y's, etc. Right? So for all x and for all y, okay, you would get your two-dimensional non-homogeneous points. If I combine with all the points on the line at infinity, you would get, okay, you would get your homogeneous coordinates. Okay, so that's the definition of these homogeneous coordinates. But the thing is that we have a singular point. It is this point. Do I have a slide for that one? No. This vector, this homogeneous vector, okay, this is not in homogeneous coordinates because this doesn't mean anything, okay?
What is the difference between homogeneous coordinates and non-homogeneous coordinates?
I mean the points, the two-dimensional points that they teach you in high school, they are all homogeneous, okay? This is homogeneous, these are non-homogeneous. Okay. Anything you have learned up to this point, they are all in a non-homogeneous coordinate system, and we represent them with R2. P2 corresponds to, okay, there is a one-to-one correspond. This equation says that, okay, for every R2 there is a P2, okay, but there are more P2s that R2 cannot represent, which are the points at infinity. Other than point 0, 0, 0. 0, 0, 0 is not in P2 because 0, 0, 0, it doesn't make any sense. There is no such thing as 0, 0, 0. Okay? It is not even at infinity. Okay? So 0, 0, 0 doesn't make any sense. Okay? So can you sign this one? Good. So up to now, we have been using this R2s. Now we are going to use P2s. I mean, this 2 should not confuse you. It's a three-dimensional vector. Okay. R3 is a three-dimensional vector. This one represents a three-dimensional point, non-homogeneous coordinates. P3 is in homogeneous coordinate system, but it's a four-dimensional vector. So I added one more dimension. That's what I did. So this is how you go from non-homogeneous coordinates to homogeneous coordinates in 2 dimensions and in 3 dimensions. How do I come back? To come back from homogeneous coordinates to non-homogeneous coordinates, okay, then I would just divide this x by w, y by w. That's what I would get for 2 dimensions. For 3 dimensions, it is this. That's why it is not sometimes possible to come back from the homogeneous coordinates to the non-homogeneous coordinates because w might become 0. We should present lines at infinity. Okay? So, in homogeneous coordinates, line or points at infinity is no different than points is no different than from any other points. That's why we like them. That's why we can do anything that we like. That's why, I mean, in 2,000 years ago, when they defined the rules of the geometry, okay, there are a few simple rules. They say that, okay, one of the rules are parallel lines, they don't intersect. That's what one of the rules in geometry, right? The other one is maybe this one. This angle and this angle are equal, right? If you intersect these two. And somebody said in beginning of the 20th century, somebody said that I don't accept that the parallel lines don't intersect. Okay. My new mathematic, my new algebra that I am defining now, it calculates the points at infinity. That's what you are calling it as point at infinity. So I reject this rule. Parallel lines don't intersect. Parallel lines, they intersect, and I'm going to give you the formula. So it works, okay? So it was kind of a revolution in mathematics, and people started having theorems like these, many more like these, and they started talking about whatever you assume. If it is not true, then there would be other kinds of nice mathematical formulations that are useful, and this is one of them. Okay.
Sir, so this geometric rule will be not applied for infinity, like maximum or minimum physical things.
Well, I mean, how do you do mathematical derivations? I mean, you assume a number of things. You say that I assume this and this and this. Assuming this is my theory. You are going to get that, and there is a proof, and that proof assumes whatever they say, your assumptions are true. Okay. In more stronger mathematical models, you say that I am not going to assume that. I am not going to assume that the lines that are parallel to each other don't intersect. Okay. They may intersect, and my mathematical formulations allow that one, and I can turn up something useful out of it. Okay. Like the complex numbers. Somebody said that previously people used to say that there is no square root of minus negative numbers. Somebody said that no, I am going to assume that there is one. Okay, the square root of minus 1. And I'm going to define mathematical rules for you that will let you do the algebra on these numbers, these kind of, I'm going to call them complex numbers. And they will be useful to analyze some polynomials, some formulas to find their roots, and it turns out that that's really useful. Okay. So again, the trick is here. I mean, let's represent each real number by two numbers. Okay, not just one, by two numbers. So each one-dimensional real number will be represented by two-dimensional numbers, and that would be the trick. Okay. And that makes lots of things possible now, which used to be impossible. And we are doing something like that. So homogeneous coordinates, we are going to use that a lot. That will make our job easier in terms of linearization of the camera geometry. Also, it's going to make it possible for us to talk about points at infinity, which will be very useful too. Okay, with the homogeneous coordinate system, there is this rule of duality. Okay, usually we represent points with x and lines with L, and if this point, okay, is on line L, the dot product between them is 0. Okay, or if this point x is on line L, the dot product will be 0. But if you see, I mean, I can just interchange these two, right? X and L, doesn't matter. So both of them are three-dimensional vectors, and if I do the dot product between two three-dimensional vectors, I get a 0. I mean, X could have been a line, L could have been a point. So what is the difference between them? There is nothing. So this is called the duality principle. Whatever you can say about the points, you can say the same thing with the lines too. So that's called the duality principle. The same thing again. If I cross product 2 points, I will get a line. If I cross product 2 lines, I would get a point, right? So the formulation is exactly the same. So any theorem of two-dimensional projective geometry, there corresponds to a dual problem, okay, dual theorem, which may be derived by interchanging the role of points and lines. Okay, if somebody says that if you cross product 2 points, you will get a line, then you will say that what happens if I cross product 2 lines, okay? Then you are going to get a pain because you are just using Control H to, it's like that, right? You are using Control H to replace each line by a point and each point with a line. That's called the duality, and we are going to use that. Okay, so far so good. That was all the definition and nice things. Let's use them in a useful place in our camera geometry. Let's talk about these projective transformations. This is what we are going to do. This is a homogeneous point. This is another homogeneous point. Okay? If I multiply this homogeneous point with these bunch of numbers, a matrix of 3 by 3, I get another homogeneous point. Okay? And the same thing, if this is a line, then this is a line too. Principle of duality, right? Principle of duality. This is called projective transformation, and that's the definition here. It's called the projectivity is an invertible. Okay, what is an invertible?
Ters çevrilebilir.
What's an invertible? Ters çevrilebilir, but what's an invertible? What is ters çevrilebilir?
We get the input of the from output if we apply this method once.
Oh yeah, okay. I can go vice versa, but I'm talking about the invertible matrix. This is an invertible matrix. What does it mean?
It's a square, and it must be square. And if you apply the 90-degree transformation and multiply, you get
Transpose, you mean? No, it doesn't have to be transpose. No. If a matrix A is invertible, then you can get the inverse of it. And if you multiply these two, you would get the identity matrix. Okay? If you can get the inverse of this matrix, that's an invertible. Okay, so it doesn't have to be, it cannot be a singular matrix. So it should have a matrix rank of 3, and this determinant should be non-zero, right? Determinant should be non-zero. So if you remember determinant is non-zero. So here we say that a projectivity is an invertible mapping H from P2 to itself. What is P2? It's the homogeneous coordinate system, right? From homogeneous coordinate system to further homogeneous coordinate system, such that 3 points x1, x2, and x3 lie on the same line if and only if h, x1, h, x2, and h, x3 do. So mapping this, so we are saying that this is a projectivity. If I project 3 points, this one, another one, another one, and if these 3 points are on the same line, in the other world, they will be on another line. Whatever that line is, doesn't matter, it's a line. Okay? So this is a projectivity, okay? And there is a proof for that one, but I'm not going to talk about the proof. Sometimes we call this a projectivity, sometimes we call it collineation, sometimes we call it projective transformation, sometimes we call it homography. And most of the time I'm going to use this homography. So homography is in two-dimensional world, okay? It is a 3 by 3 matrix, okay? It will transform us from one two-dimensional space to another two-dimensional space. So why are we talking about this? We are talking about this because with the homography we can do this kind of stuff. This is a two-dimensional plane. This is another two-dimensional plane. And this theorem says that, okay, there is a homography between these two planes, okay? See, this is a point X, right? This point X. If I do this, I will get x prime. Okay? And vice versa. If I do this, I will get x. Okay? So if somebody says that I have an object on this one, I have a picture of a man like that. If I transform all the points of this picture, you will end up with this picture here. Okay? Because there is a projectivity defined between these two planes. This is one plane, this is another plane. Okay, this is a two-dimensional world. This is another two-dimensional world. Okay, between two-dimensional worlds, you can define these projectivities. And these projectivities will keep lines as lines. Okay, lines will stay as line because that's what it says. Okay, line will stay as line. It's a projectivity homography. And to define homographies, we can use this 3 by 3 matrix. It says that this 3 by 3 matrix is 8 degrees of freedom. What does that mean? There are 9 numbers, but it has a 8 degrees of freedom. Okay, but how about this one? I have a let's say a flexible string. I can make this stretch it, I can make it longer, or I can make it shorter. So I can make the string longer or shorter. What is the degree of freedom of the movement of the string? How many degrees of movement are possible?
6.
What?
6.
Just one, not why 2? Either I can go plus this dimension or minus this dimension. Just 1 degrees of freedom,
Up,
right?
down, inside, outside.
What?
Inside, outside.
What do you mean inside, outside?
And z-axis.
So I have only one ax. I can make this short or long. That's
Okay,
it.
in one axis.
But if I have in 2 dimensions, I can make this point go anywhere, like make the string longer, shorter, or change this theta 2. I have 2 degrees of freedom, right? Here I am talking about 8 degrees of freedom, but I have 9 numbers. Can anybody tell me what's going on here? I am using, here I can say, make this longer plus 5, or make this shorter minus 2, right? Here I can say that, make it longer plus 2, and increase this as 30 degrees more, 2 numbers, 2 degrees of freedom. But when I come here, I have 9 numbers, but I'm talking about 8 degrees of freedom. What does that mean? I mean, remember, can you connect this with the homogeneous coordinate system rules? Remember what happens with the homogeneous coordinates? Let's go back there. Let's go back to the homogeneous coordinates. Yeah, here it is. Remember this? ABC, if ABC represents a line, K times A, K times B, and K times C represents the same line too, right? So ABC and KA, KB, KC are the same thing, right? So if I do this, okay, so K times x1, K times x2, K times x3, it will be the same as this. Or instead of doing that, if I multiply each of them by K, it will be the same projectivity, right? So, I mean, if 2 projectivities, they are similar to each other up to a constant like that, up to a K, we consider them as the same projectivity. That's why I need only 8 numbers, not 9 numbers to define a projectivity. That's why it says 8 degrees of freedom. So I can do this. I can divide each of these numbers by h33, right? I can do this, right? So if I divide each of them by h33, it is the same projectivity again, same homography. And this one, the last number becomes 1. All I have is just 8 numbers. So 8 numbers would define a projective transformation or homography. Okay? That's why it says 8 degrees of freedom. Good? And I can define these projectivities between points, like between planes like that. Okay, what else? Okay, so let's look at this picture. This is a picture of a wall. Okay, and since I have taken this picture from the real world, let's look at these two lines, line number 1 and line number 2. As you see, if I go even further like that, they are going to intersect at somewhere, right? Okay. Why is this happening? Because the perspective transformation, because of the effect of the lens projection, right? Nearby objects seem larger, far objects seem smaller. And if you have these kind of parallel lines, and it looks like they are going to intersect in some place if I continue like that. Okay? And the same thing might happen with these lines too, because they are doing the same thing like that. Okay, they are going to intersect somewhere above the image. So I don't want to see images like that, but I like to see images like this. In this case, see, if you see this one, let me get rid of this one. So all the parallel lines, they seem like parallel, right? And all these are parallel too. Okay? How can I get an image like that out of an image like this?
Transformation.
What's that?
H transformation.
I don't understand what you have just say it louder.
By multiplying matrix H.
H. So I should come up with a matrix H that which they should transform all these points from this image to that image, right? But how am I going to do that? Let's do this. Okay? This is how we are going to do that. I know that the difference between these two and the difference between these two should be equal, and the difference between these two and difference between these two should be equal, right? Okay? If I say I should transform this image to such a window, I know that this point will correspond to this one, and this point will correspond to this one here, and this one is here, 4 of them. So in my ideal image where I know that these are the things, so I would say that, okay, this is my 100 by 100, okay, this is x is, okay, 100 by 90, okay, and this one here is 120 by 90, and this one is 120 by 100, right? So hypothetical image, and I know the coordinates of these 4 points. So I have 4 points, and I should define so what are my points? P1, P2, P3, and P4. I know that when I multiply this P1 with this H, whatever that H is, I should get 100 by 100, right? And if I multiply this H with 2, I should get 100 by 1. What was it? 100 by 90? Is that correct? 90. And 120 by 100. and 120 by 100. No, 90.
Is this 8 degrees of freedom?
Okay, H and H. Yes, H is always 8 degrees of freedom. So how many numbers are there in H? There are 9 numbers. Okay, there are 9 numbers, but it looks like I made a mistake in there. Maybe I should have done it this way. Move it a little bit there. Okay. So equals. So tell me what's my problem is. What's my problem?
It's 2D.
Yeah, these should be all homogeneous coordinates. 1 and 1, right? So P1, P2, P3, and P4 are in homogeneous coordinates. Okay? So multiply P1 with this H, I get this one. So H has 8 degrees of freedom. That means that I have 8 unknowns. How many equations do I have here? And to solve this 8 unknowns, I need to have a certain number of equations. To solve for 8 unknowns, you need how many? You need 8 equations. What's your name?
Abdurrahman.
Why don't you speak louder?
We need 8 equations.
Okay, we need 8 equations, but it looks like I have only, what? 4, but where am I going to find all the rest? So you may say that, why don't we use more points like that? Okay, maybe I can get 4 more points, okay, and these points will correspond to these points there. I can solve it, but my answer is no, you don't need it. 4 correspondences are enough. So if you have 4 correspondences between this picture and this picture, that will be enough for you to get the homography. So how is this possible?
You can generate lines or vectors via using points.
But that will not give you the correspondence, so that will give you only a line. You don't know where you are at with that line, right?
Is it because this is a 2-dimensional space?
Well, even if it is 2-dimensional, you need 8 unknowns. You need 8 equations. I have only 4. You are not looking at the equations correctly. What is H? H is a
Matrix.
3 by 3 matrix, right? So let's look at this one. So H is this from H11 to H33. This is P11, P12, and P13. When I multiply it to the other side, I should get 100, 100, and 1. So this is just one equation, H12, H13. So I should multiply H11 times P11 plus H12 times, let me use this dot sign, okay, P12 plus H13 times P13. This will be equal to 100. So I get an equation out of this multiplication. Multiply, okay, multiply this line with this vector here. I get one equation. For the second equation, I am going to multiply this one with this again, and for the third one, I am going to multiply this with that one. So I am getting, right, 3 equations out of the this simple line, simple point correspondence. So if I do that, I will get whatever I want, and I will solve this parameters for H, and I will get my homography between these 2 images. Okay. Let's try to see what the book says. I get this slide from the book. The book says that, let's try to understand this. If I multiply, can you understand? Let's look at this one. Can somebody read this one for me? This one. What is x and what is x prime? What is x? What is x1 prime? What is xt prime?
Is it slope? Slope?
Which one? What is x? Are you talking about x?
x1 prime over x3 prime.
It is what?
Slope. Slope.
I don't, can you?
Slope. A.
Oh, no. Well, you could say it maybe that way, but no. Well, this is just a point, right? Points don't define slopes. Lines define slopes. No, I'm not asking this one. I'm asking about x and x prime. What is x and what is x prime?
X is the normal real image. X prime is the projection. Point. Point in the real image and.
Well, no. I mean, see this one. H11 times x, H12 times y, H13 times 1. So this one is in homogeneous coordinates. And this one is in homogeneous coordinates too. So let's try to write it more carefully then. It's like this. H times, maybe use a blue pen so that H times, let's say, my point P. My point P is x, y, and 1. Okay? So H times x, y, and 1. What is H? H is H11, H12, H13, H22, H33. This is x, y, 1. Okay, so what would I get out of here? It would be H11 times x plus H12 times y plus H13, right? And the second line is H21 x plus H22 y plus H23, and the third one is H31 x plus H32 y plus H33, right? So this is my homogeneous point in my left image, and this is my homogeneous point in my right image. Okay, but if I like to go from homogeneous point to the non-homogeneous point, this is what you need to do, right? You need to divide this by this. That's what it's like. Okay, I am going to divide this. Okay, this is okay. I am going to divide this H11x, H12y, and H13 by the third one, right? So that will give me my x prime. X prime is the non-homogeneous point on the right image. Here, this one. Okay, so that's what the equation says. Okay, and I can write the same thing for y prime. And if I do the math, okay, this is x prime, this is y prime, and I can write x prime this way, and I can write y prime this way. Okay. So here I am after h. I know the x's, I know the x primes and y primes. I need to find these numbers. Okay. So write a linear equation to find these numbers and solve for it. And using these 4 points, you can get the projectivity or the homography. So I can get a homography between these two. and once I get to homography, I can transform all the pixels from this space to this space. So question for you, why are there blacks in here? Why is there a black and you don't see anything here? But there is nice brick pixels here, but these areas are all black. Why are they black? Why didn't they fill them in?
Lack of information.
What do you mean by lack of information?
The original image doesn't come.
Who is talking? Okay, yeah.
Because we changed the angle, so the image should be different. And we
Well, intuitively you can explain it this way, but talk to me in terms of this projectivity or the homography H.
x1 prime is 0. It's obvious because x and y represent that point is 0.
Say it again. What is 0?
X1 prime is 0 and x2 prime is 0 for that point, and it represents 0.
Why do you think it is 0? How about this point? It's not 0. Okay, let's look at this one. Here, x1, x prime, okay, is let's say 100 and 120. Okay. To find the corresponding point, this x prime, what do? We multiply it with h. It's going to give us 1x, right? How about this one? Let's do this. Tell me the coordinates for this point. Let's say this is 100 by 100. Okay. Let's say this is 100. Use a different color. Okay. For this point, it is, let's say, 100 by 100. Let's say this is our point R. If I multiply this R with H, I should get this point, and this point looks like it is 110 by 100, something like that, right? So if I multiply this R with H, I should get this R prime, and R prime is, you know what I get, okay? Of course, I should be, these all should be in homogeneous coordinates, okay? So this is how I do it. I multiply the position of this R prime with H minus 1. I get 100 by 100. Whatever this pixel value is, I put it in there. But how about these places, these black positions? Why couldn't I put anything? Because let's look at this one. I know that this point here, let me use the red color. This point corresponds to this point here, right? How about this point? This point then in that case is going to correspond to this point here, which is outside of my image. I can do the transformation, but I cannot reach a valid image position because this is out of my image. That's why I cannot put anything in there. Right? It is all black. That's why it is black. I cannot complete it. I don't have that image data available for that position. Okay, that's why when you do this kind of corrections, sometimes you get this kind of black areas. To prevent this, sometimes people would just take only this part of the image. Okay, so you lose some part of it. And as you see, this is a perfectly rectangular image with all the windows, right? With all the windows. So basically, if you go back, if you are given an image like that, and if you know the parallel lines in this image, I know that, okay, I know that this line is parallel to this line, and I know that this line is parallel to this line, okay. although on this image these don't look like parallel, I can make them parallel in another image. That means that get these 4 points, okay, define another image, in that image make these points perfectly rectangular and transform it. Okay? So this is one case where we use the homography. Okay? This is a case where we use the homography. Another example is this one. Okay? This is a camera that takes the picture of this plane in the real world. Let's say this is a soccer plane, futbol sahası gibi düşünün bunu. Let's say this is a soccer plane. Okay, soccer field. These are my lines. Okay, this is my line 2, like that. And this is my center circle. Right? What else? I have these. Good. Okay. I have a camera. I took this image of this plane. I have another camera. I took this image, a picture of this plane. Okay. I know that there is a homography between this plane and this plane. Also, there is a homography between this plane and this plane. Right. That means that I can define an homography between these two, because why? Let's say this is pi, plane pi. This is C1 and this is C2. If there is a homography between pi and C1, and if there is another homography between, okay, C2, then maybe I can do this. Okay, I will say pi is equal to H1 inverse times C1, then C2 is H2 times H1 inverse times C1. Okay? So I define the homography between these two images. Okay? So what does that mean? On this camera, if you give me a point, I can translate it to this camera position. Okay, very, very convenient, very, very nice way of looking at the soccer field. And this is going to be one of your homeworks again. So I can look at the image plane. I can look at the soccer field in any camera position that I like. Right? Of course, I am assuming that this is a plane, right? Soccer field is a plane, but the players that play on it, they are not part of the plane. They are above the plane. So my equations are going to work for the plane, but not for the players, right? Because players are above the plane, they don't belong to that plane.
Can I ask a question?
That's why we need to do something about the players. But for the soccer field, we can do whatever we want. Yes.
Are two eyes see intersection image?
Yeah.
Is it these kind of?
You are asking this question. Okay. I have two cameras. Their center are the same. They are looking at two different directions, right? That's what we are asking. So there is a lot of overlap between these two cameras, right? There is a lot of overlap between these two cameras. But I know that this point corresponds to this point corresponds to this point, and there might be other correspondences too. So I can define a homography between this plane and that plane too. Okay? In this case, I don't need to be seeing the same plane between these two images. Okay? Any other questions? So these are all possible because of the homography, and homography is possible because of the homogeneous coordinates, because when I go to the 3x3 matrices like that, using on a two-dimensional world, if I define everything in three-dimensional notations, homography is possible. With the homography, these kind of things are possible. with these kind of things, we can do many things that you think that not possible. That we can achieve things that might surprise other people. That's what I'm trying to say. Okay. Are there any questions?
Now,
Yes.
in the previous example, how do we set the age parameters? Like age
You mean this one?
In the previous example.
You mean this one?
Yeah. How do we set the age parameters? Age 1, age 2, 1.
How do you? Well, I mean, you have 4 equations. You have these 9 equations and you have 8 unknowns. It's a linear system, right? You put them together and you solve it. What did we do here? Okay, I know x's, I know x primes, right? I know x's, I know y's, I know x primes, and I can write 9 of them, or 4 of them, 4 pairs of them, one after the other one. So I have 9 unknowns and I have 9 equations and I can solve it. These are linear equations. Okay, so we will come to that in a few minutes. Actually, we will. How can we say that? Maybe we will. I'm going to give you one example where, or maybe I should do this. Practically, without doing anything in mathematics, I am going to tell you that, okay, use OpenCV. Yeah, okay. So in OpenCV, there is a function named find homography. Okay. You provide 4 2-dimensional points, source points, on one image. You say this point and this point and this point and this point. Okay, these are the image number 1. This is the image number 2. This point, this and this and that. Okay, I know that this one corresponds to this one. This one is here, this one there, and this one is there. Okay, I know this. Okay, I know these correspondences. So you say that for the source points, I am going to give you these 4 points for the source points. Okay. For the destination points, I am going to give you these 4. Okay. You are going to, let's ignore this one. You are going to run this function and you are going to give me 9 homography parameters, 3 by 3. Okay. And you will get this one, and that will give you the homography, that 3 by 3. So how does this function work? It is nothing secret. It just solves a linear equation, and you know how to solve the linear equation, either Gaussian elimination or singular value decomposition or anything you like. It is not a very complicated equation. Okay? So, I mean, some part of your, some answer to your question, obviously very superficial, without telling you what's going on inside. You call such a function. But what's going on inside the function, again, it is simple. It is just, you have 8 equations, you have 8 unknowns, and you are going to solve a linear equation system. Linear algebra. Okay, good. I need to take a break now. Let's take a break for 15 minutes. Please open the windows. Keep it open while we are taking the break. Then we will come back.
Hocam bu derste lineer cebrin tamamını kullanacağız diye.
Lineer cebrin tamamını kullanan insan var mı dünyada ya?
Şey diyecektim, lineer cebir dersi vereceğine computer vision'ı verseler daha zevkli olur diye.
Lineer cebir dersine, computer vision dersine verseler, ertesi gün cimerden 20 tane dilekçe gelir. Evet. Çünkü önemli olan en az şeyi öğrenerek diploma olmak. Tamam mı? Çok şey öğrenerek diplomayı herkes alır.
Ne olur?
Yani lineer cebiri kullanan sadece vision yok ki. Kimyacılar kullanıyor, haritacılar kullanıyor,
Ben de bir şey
kullanıyor.
çok kalemle kullanarak çok kısa. Hocam şöyle mesela ilk verdiğimiz örnekte bir tane line şu şekilde geliyordu. Bir tanesi de bu şekildeydi.
Evet.
Bu işte bizim source'umuz. Destination'da da bu ikisini de böyle yapıyorduk.
Paralel yaptın, evet.
Evet.
Ben seçtim ama destination'ı.
Evet işte destination mesela seçerken asıl sormak istediğim soru oydu. Yani destination mı
Paralel
seçiyorsun?
paralel kalsın diye seçtim o. Yani öyle bir şekilde olsun ki
Mesela
bunlar
şurası, diyelim ki işte burası 3'e 3, işte burası da 3'e 5'e 3.
he,
İşte bu ikisini mesela hani sonrasında olması için mesela burayı da yine aynı 3'e 3.
3'e 3 yap, burayı da 5'e 3 yap.
Evet.
Öbür taraftaki seçerken orayı 6'ya 3, öbürüne de 8'e 3 seçmem lazım.
Bu şekilde seçince bunun para yani hepsini ona göre.
Tabii görüyor musun? Aradaki fark böyle kalıyor. Şurada daralıyor, orada daralmıyor.
Tamamdır hocam. Şimdi anladım.
Tamam.
Teşekkür ederim.
Bu dersin WhatsApp grubu var mı acaba? Dersten alıyoruz da.
So the homography is something very useful. If you have two planes, you can achieve a homography between two planes. But our world is three-dimensional. In three-dimensional world, if you are dealing with the planes, homography is okay. But if you are dealing with three-dimensional, real three-dimensional points, then homography will not be good. So if we see these constraints, then we are going to use it a lot in many examples. This one, for example, this one is good because the face of this building is a plane. Okay, this is another plane. So I can do the plane-to-plane mapping with homographies. But if I have such an image, such a building, but I don't have the plane of the building, then this will not work, of course. Okay. So we will come to this and we will talk about it. We will talk about this in your homework. We will talk about this when we do the image stitching, okay? And we'll come to those. So let's go back to this perspective projection again. So we were discussing perspective projection previously. Okay, that's what we were doing. Okay, we said that, remember this one? We said that this point XYZ, if I wanted to project this on this projection plane or image plane, here, this is the formula, right? Using the similarity of the triangles, I can say that, okay, transform XYZ to X over Z times D minus D, and X over Z times D minus D, and put them together, and now I have this formula. So I can transform these 3 points into these 2 points. So divide it by Z and multiply it by D. We like this. These are called projection equations, but there's a problem with this kind of approach. This thing is not linear because we are dividing it with Z. I like to linearize it so that I can do linear algebra on them, basic linear algebra on them, and that's why we veered into homogeneous coordinates. Now let's go back to this projection and let's try to see how the homogeneous coordinates help us to achieve this. So basically we are going to do this with a linear matrix multiplication using the homogeneous coordinates. Okay, so if this is my three-dimensional world, and if I put a 1 at the end, this is the homogeneous point, okay, in three-dimensional world. If I multiply it with this such weird-looking matrix, 1 0 0 0 0 1 0 0 and 0 0 1 minus 1 over d times 0, this is what I would get, right? So this is kind of making a four-dimensional vector into a three-dimensional vector. But if I take this as a homogeneous coordinate in two-dimensional world, so how do I go to non-homogeneous coordinates? Like doing this one. Okay, so x over z over d, so minus d times x over z. Okay, so if you divide this x with this number, this is what I get. If I divide y with this number, this is what I would get. Okay, so I achieved what I wanted. Okay, so I am using this matrix multiplication to achieve the perspective projection. So everything is linear. So this is a 3 by 4 matrix, and this is a four-dimensional vector, but it is in P3. Okay, this is P3. But as you know, the vectors in P3 are four-dimensional, and this is a 3 by 4 matrix. And multiply this vector with this matrix, and you achieve the projection. I can do it in many different ways, but the idea is the same. Always start with the homogeneous coordinates and multiply it with some kind of a matrix. Sometimes people do this too. It's the same thing. Okay, so diagonal matrix, but here I have minus 1 over d. Okay, again, this is a matrix in homogeneous coordinates. I can multiply this matrix, the whole numbers of this matrix with a constant, that the result will not change. So maybe I can multiply with all of them with d. So this would become d, and this is multiply it with minus d. So this will be minus d, and 1 here. Okay, it could be that way too. Okay, so it would be either a 4 by 4 matrix or 3 by 4 matrix. Both of them will work. I will end up with the same numbers. Okay, so again, what did we say? Perspective projection equations are not, but they are not linear. Now I linearize it. I can use the linear algebra to do this kind of stuff. Linearization is very nice. See this one? What did I say? I can transform any point on the C1 to the C2. How do I do that? I calculate the H between these two. I calculate H between these two. And what is this H2? It's a 3 by 3 matrix, right? This one is a 3 by 3 matrix too. So this one is again H3 is a 3 by 3 matrix too. So linearization have these kind of advantages. Now this 3 by 3 matrix, this is 9 numbers. Those 9 numbers can achieve this transformation from this space to that space. Okay, so linear algebra has these kind of nice properties, and we are going to use them. Okay. Any questions up to now? Okay, no questions. Then I will continue. If there are no questions, this is our perspective projection. In perspective projection, again, if you have a cube, okay, let's say I have a cube. So the front of the cube is like that, but usually we draw it like this, like the back side of the cube gets smaller like that, right? I mean, I know that this length L and this length L is the same, but if I project this cube onto my image plane, okay, this is an L, not T. They are the same, but on the images, the far away objects or the far side of the object, they look shorter. Okay, this is the effect of the perspective projection. If I don't want this kind of projection, if I like to see my lengths, I mean, if this is L and this is L, okay. If I like to see the equal lengths should be equal on my images, then what we are going to do is the orthographic projection. With the orthographic projection, the relative lengths don't change, okay. In the real world, if this is my triangle, in the image world, it's going to be the same way. But still, I am going to two-dimensional, not three-dimensional, two-dimensional. If you are doing the orthographic projection, okay, or the parallel projection, this is your projection matrix. 1, 1. Remember, if I do it the other way, it used to be 1, 1, and 1 over D here. Now I don't have it. 1, 1, 0, and 1. What happens here? This Z is always multiplied with these zeros. So Z is ignored, right? Z always is ignored. So I end up with X, Y, 1. So this projection is possible again in the homogeneous coordinates. Okay? So orthographic projection is also is something possible that we can do with the homogeneous coordinates. Okay? By the way, this kind of a lens is available. It is called telecentric lenses. Okay, let's look at this picture. Okay, you see the effect in the real world. This is my camera. These are the objects. If I take a picture of this scene with a conventional lens, this is what you would see, right? So although in the real world these three cubes are the same size, right? I see this one large, this one is small, and this one is smaller, right? What is the problem with it? The problem is this. If I like to inspect these three cubes, and if I say that, okay, this one is equal to this one and this is equal to this one, their sizes, so that I can inspect them, with the conventional lens this will not work, because I cannot make a differentiation between the large objects and the small objects and how far they are. But if I use a orthographic projection or the telecentric lens, this is what I see. Okay, this is what I see. So there are telecentric lenses like these. Okay, and they are kind of expensive, but they are very, very useful. These telecentric lenses, using some kind of a technology, they do orthographic projections. And I think, do I have good examples of telecentric lens examples in the main. Lenses, what?
Hocam Edron'dan bağlayabilirsiniz.
So that means that the people. Oh, okay. Can I go back? Okay, we are recording it and do that. Okay, so let's go to the Google again, telecentric lenses, and let me show you one example. That is usually this is a good example. So they took the chessboard, they where is it? Okay, so this is a chessboard. If I take the image of this board using a conventional lens, it means what? This distance here, this much, should be equal to the distance there, right? But because of the perspective projection effects, okay, I don't see them the same. How about this one? At the below image, this distance and that distance is the same. So my measurements, they don't depend on the depth anymore. Okay, whatever the depth is, my distances will look similar. Also, the height of this pound is larger than the height of this pound here, but in this case they are all the same. Okay, so they are very useful for industrial kind of applications when you do the measurement. These kind of lenses are doing orthographic projection. Okay, these kind of lenses do orthographic projection, and for the orthographic projection I can use this projection matrix. Previously I was using this, okay, minus d1. This is the perspective projection. With this one it is 1, 1, 0 and 1 here there. Okay, these are all possible because of homogeneous coordinates. And sometimes I do it this way. How about this one? Can you read this one? Read it to me. Tell me the effect of this kind of an equation. Can I make it this? Okay. What does it do? It ignores z. But z is gone. That means that it is not perspective. It is orthographic, but it is not pure orthographic. It divides all the x and y's with a d. Okay, so it is scaled orthographic projection or weak perspective. Okay, some of the lenses they do this. Okay, good. And as a final example, we have a fine projection. I mean, we don't have these kind of cameras, lenses. They are very difficult to build. So there is no structure to it, okay? And I multiply this number with this point with this matrix, and that's all I do. These are all independent numbers. This is called perspective. It is more than perspective. It's affine projection. So, what is affine projection? Affine projection is, well, I think I'm going to show you some examples of it later. Okay, I think I'm going to show you some examples later. For example, with the affine projection, you can project this kind of a rectangle into this kind of a shape. Okay. So parallels stay parallel. Okay, but you lose the angle information. So your perpendicular lines, they are not perpendicular anymore. With the perspective transformation, okay, with the perspective transformation like this, you lose both parallelism and the angle information, relative angles between them. The only thing that you keep is the linearity, line stay line. Okay, so we will talk about this later. Okay, let's go back to our original picture now. Remember this one? If I project this XYZ on this image plane, okay, X prime, Y prime, and Z prime. If I project it, okay, this was by the way, I kind of changed the notation a little bit. Previously, my image plane used to be in front of the central projection. Now it is behind it. Doesn't matter. Only this minus D becomes plus D, and my images are upside down now. But that's okay, no problem. So this is what happens: X prime, Y prime, and Z prime here. Z prime is, I know it is F prime. It is the distance of this image plane pi prime from the central projection. O. Okay. So my X prime is related to X by this lambda, and lambda is in this case both of them, they are all equal. Lambda is in this case X prime over X, or Y prime over Y, or F prime over Z. I know this one, so it is F prime over Z. So X prime is equal to X over Z times F prime. Okay, so previously we did that. Okay, we said that X over Z times minus D, this is F now. Okay, so this is the equation of the projection, and we know how to make this work in terms of matrices using the homogeneous quadrilaterals and 3x3, 3x4 matrices. Okay, basically the same thing. So we are going to talk about now in the camera world how this thing is going to work. So far we work on this kind of normalized image planes. We assume that there is an image plane and our point is projected to this one, and for this one our equations are like those. But in real world we don't talk about image positions as millimeters. Like, we talk about image positions in terms of rows and columns. Okay, we say that okay, this point is at position 100 and 100. That's what we say. Okay, and we have to relate this to this normalized image plane, and this is what we are going to do in a few minutes. Okay, so our images come from this physical retina or physical CCD sensor. Okay, in that one we have an origin which is different than origin of the our coordinate system. It is different. Okay, and sometimes we don't have perfect 90 degrees between this axis and this axis. It is maybe 90.001 degrees, maybe 89.99 degrees, I don't know. Okay, so I have to take these kind of constraints into into consideration, and I will have to use again the matrix multiplication stuff to model this what's going on. So many things that needs to be considered. For example, what did I say? These columns, okay, and these rows. How many columns and how many rows you have is an issue, right? Let's say if I have 100 rows and 100 columns, this one is going to produce a 100 by 100 image. So this width is important, okay? How wide is my pixel and how high this pixel? These are the two questions that will come to the picture, and I will have to use them, okay? Also, how far I am away from this origin, that's important. This theta, is it perfect 90 or a little bit different from 98? That's important too. So I am going to put them all into perspective, and I will write formulas for those, okay? I know how to get from this P to this P hat. It is simple perspective equation. I get this P, X, Y, Z, put a 1 beneath it. Okay, so this is a 4-dimensional vector now. What is this ID? Can anybody tell me what this ID is? It is identity matrix, okay? So if I open this up, it will be 1 0 0 0 1 0 0 0 1 and 0 0 0, okay? Multiply it with my real world point x, y, z 1, okay? So this 0 is actually a 0 vector. These three numbers correspond to this one, okay? And this is the ID. Multiply it with this one, divide it by z, and you get the p hat. Okay, you are going to say that, okay, this is linear, but it's not linear. But I told you how to make this linear, right? I told you how to make that linear, because, I mean, if you do that, if you multiply it, if you convert this, whatever comes out of this one into non-homogeneous system, this is what you're going to get. And basically, this is what you're going to get. U hat and V hat, U hat and V hat. If I ignore the focal length, let's say here, this length is just 1.0, then in that case it's going to be x over z and y over z. Okay? So I know how to get from this point to this point to this point. But how do I get from this point to that point? This is what we're going to do. Maybe I should keep both of them on the same slide. Yeah, that would be a better solution. And you see it now. Maybe I should do it. Just a minute. Here, there, no, this one, that way. No. There must be a place where it says page. No. Show it as 2 pages, double pages. Did you guys see it? Double pages somewhere. Is it here? View. Yeah. Yeah, it should be double page, and I don't want to come to this point now. Is it? No, I am not going to mess it up. No, sorry. I will keep it that way. Get it, go away. Okay. So this is the equation, but I like to go to u and v. This is u hat, This is V hat. Okay. I am saying that. Okay. There is a similarity. Let me get rid of my stuff. Okay. There is a similarity of the triangles between, okay, this length and this length, right? Also similarity between here and there. Okay, I know this much. This is a total of F. This is, okay, U hat, and this is U. But how about this one? I mean, where am I? I don't want to use the millimeter units anymore. I wanted to use the row and column numbers. Okay, row and column numbers. How am I going to introduce them into the equation? This is what we are going to do. This K and L, okay, F is the focal length. It's the how far I am from the origin. K and L, okay, K and L are the widths and the heights of the pixels. Okay, they are physical pixels. If I multiply them with this F, and if I multiply that number with x over z, you would get the U coordinates. Okay, so U is talking about the number of rows, V is talking about the number of columns, okay, because now I have discretized them, and by multiplying this F with K and L, I get to talk about U and V. But still, my 0, 0 point is here, because 0, 0 used to be here, right? It's 0, 0. I don't like it, because sometimes I want to make my 0, 0 number here, the corner here. Sometimes I like to make it 0, 0 here. It depends on me. So what am I going to do? If my 0, 0 is here, somebody should give me the length of this vector as U0 and V0. U0 and V0. Okay? So if this is given, I can add this U0 and V0 to my equation over there, and this is what I would get. By the way, alpha is K times F, beta is L times F. Okay? So my equation becomes this. As you see, this is not a linear equation, of course, but you know we are going to find ways of linearizing this later in a few minutes. Okay. So what did we achieve here? We did the projection x over z and y over z. Okay. I multiplied with k, f, and lf. Okay. I multiply them with them, and I added these two numbers. Okay, I added these two numbers. And I am not going to talk about this, but if you like to take this theta angle into consideration too, that is the skew angle, this is called skew. Okay, the skew angle here. If it is different from 90 degrees, if you like to put that into consideration, then you can do that with this formula. See, what is the sine of 90 degrees? It is, what is sine of 90 degrees? 1. It is 1. So it is going to be V is equal to beta times y over z, right? And what is the cotangent of the 90 degree? It is 0. So it's going to be alpha times x over z plus u0. Right? So it will drop down. So if theta is perfect 90 degrees, then it is this one. If it is not, then it is this one. We are going to assume that it is not perfect 90 degrees. So we are going to use this formula. Again, this is not linear, and this is how you make it linearized. Okay? This 3 by 3 matrix, if you multiply it with u, v, and 1, it will be exactly same as this one. Can we do it? Can we do it? Let's multiply it with u. This is u, v, and 1. Alpha times u. Okay, that's one thing. And minus alpha cotangent times v plus u0. u0 came from here. But what is u? u is x over z. Okay, so alpha times x over z, which is this one, minus alpha times cotangent y over z plus u0. So it is the same thing. So what did I do? I made it into a 3 by 3 matrix. Now I can multiply this uv1 with this 3 by 3 matrix, and I can get the image coordinate system. Okay. So what I am doing here is that I get a point here in this uv space. I multiply it with a 3 by 3 matrix. I get the result back in my image coordinate system. Okay. Any questions? So again, previously I defined how to come from this point to this point using a matrix. Remember, point times a 3 by 4 matrix. Now I am multiplying that matrix with a 3 by 3 matrix from this point to that point. So since these things are linear, I can combine them. Okay. So are you taking this course? Are you taking this course? What's your name? Why are you taking this course?
Yeah.
You are not listening it.
Sorry, I had to look something up.
I mean, if you don't want to listen, why are you coming to the course? Okay, so we are doing two things. One of them is okay, projecting from the real world to this hypothesized image plane, and from image plane to the from the real world to the hypothesized plane, then from the hypothesized plane to the image plane, two things, and we are going to combine them in a few minutes. Okay, don't forget about this one. Maybe make this a little bit simpler. Let's forget about this theta. If I forget about the theta, it is alpha 0 u0 0 beta and v0 0 0 1. Okay, and this is u, v, and 1. Okay, so if I ignore it, if I ignore this theta being different than 90 degrees, u and v, remember, u and v are not our xyz positions. They are projected positions. They are projected from remember, we get the uv by this 3 by 4 matrix, x, y, z, 1, and you get u, v, 1, and k. Okay, this is a matrix and this is another matrix. We are going to combine these two matrices to go from all the way from the real world coordinates to the image coordinates in a few minutes. Okay. Before that, I need to introduce a number of transformation related stuff. Basically, we are going to talk about how 3D worlds are different in terms of their transformations, but I can't do that without taking a break first. I need to take a break. 15 minutes. Are there any questions so far? Maybe I will take the question and take a break now. Okay, let's be here at around 37. Tabii.
Geri bitirme toplantısı var. Benim o saat machine learning dersim var ya.
Yarın mı?
Evet.
Yarın
8
yok ya,
Mart'ta
sen
değil
niye
miydi?
maillerine cevap vermiyorsun?
Mail.
Cuma'ya aldık ki onu.
Hocam
Herkes oy verdi, sen oy vermedin.
görmemişim hocam.
Cuma'ya aldık, senden başka herkes oy verdi. Dolayısıyla o Cuma'ya alınır.
Tamam
Cuma
hocam,
saat
zaten
üç mü?
Cuma benim
Cuma
boş
3
günüm.
mü 4 mü öyle bir şey.
Tamam hocam.
Hocam Erhan Hocam toplantısı saati açıklamış da ona bakmak zorunda kaldım.
Gelmesen daha iyi benim için. Yok, hiçbir zaman dinlemedin sen. Dersten başındaydı, hiç dinlemedin.
Hocam ben şey diyeceğim, ben Vision grubuna başvurmuştum Teams'te ama istek atmıştım. O hiç onaylanmadı benim. Bakma
Allah
şansınız var mı?
Ya ben genelde bakıyorum her gün ama. Bu değil. Bu hangisi? Ha bu. Buna da bilsen misin?
Yok.
Yok.
Bir daha bir bakayım o zaman.
Dur ben ekleyeyim hemen seni.
Ha, o da olur.
Hangisi bu? Şuradan. Şu değil mi? Tamam. Şuradan öğrenci ekleden. Üye ekle.
Muharrem Ozan Yeşiller. Aynen.
Eklenmeyen var mı arkadaşlar buraya başka?
Teşekkür ederim hocam.
Hadi görüşürüz. Ha?
Ben de
Sen de mi yoksun?
Serhat Öğüt Satıcı.
Serhat.
Agit.
Görüyor musun ismini?
Yok.
Serhat Ali Yiğit mi?
Agit. A-G-İ-T. Satıcı.
Tamam. Tamam.
Hocam merhaba,
Merhaba.
ben Reyhan.
Evet Eyhan.
Yoklama alıyor musunuz bu derste?
Evet.
Beni gruba eklemediğiniz için derse katılamadım.
Derste zaten online yoklama almıyorum ben. Yüz yüze alıyoruz yoklamayı.
Yüzde nasıl?
Yoklamayı yüz yüze alıyoruz. Buraya geliyorsun, imza atıyorsun.
Ha, dersler yüzde mi işleniyor?
Evet.
Anlamadım.
Evet, yüz yüze işleniyor dersler.
Tamam.
Tamam.
Hocam duyabiliyor musun? Selamlar.
Evet.
Berkay ben. Bu bildirim formunu size elden mi vermem gerekiyor? Nasıl yapmamız gerekiyor? Onu geçen konuşmuştuk ama.
Yo, sekreterliğe benim imzalamam lazım. Ondan sonra sekreterliğe veriyorsun.
Sekreterliğe. Tamam, ben o zaman yarın size imza atayım, sonra sekreterliğe vereyim.
Tamam olsun.
Bu yüksek lisans bildirim formu yani. Test konusu mu?
Evet, aynen.
Onu hemen vermem gerekiyor mu benim, yoksa hocam yeni başladım ya, ikinci dönem mi vermem lazım?
Hoca dışarı çıktı.
Tamam.
Benim bildiğim kadarıyla ikinci dönemde veriyorsun. Benim ikinci dönemim bu, o yüzden veriyorum ben. Sen de büyük ihtimalle bir dahaki dönem vereceksin.
Tamam. Teşekkür ederim. Peki bir şey soracağım. Dersler tamamen yüz yüze mi yoksa hibrit mi yapılıyor?
Hibrit ama yoklamayı sınıfta alıyor sadece.
Yani kaç kere gelmem gerekiyor sınıfa? Şeyden dolayı diyorum. Pazartesi günleri toplantılarım oluyor da o yüzden.
Yoklama, onu bilmiyorum, onu hocaya soracaksın. Geldiği zaman.